I'm going to now hand over to Martin Meyer from Alnylam to introduce the Lifetime Achievement Award winner.
Thank you, Annemieke. So it's a real honor and a great pleasure to be here to introduce the recipient of this year's OTS Lifetime Achievement Award, Dr. Muthiah Manoharan, who, like many superstars who go by a single name like Elvis and Pelé and Madonna, is simply known to most of us just as Mano. And I don't have time to go deep into Mano's biography because we prepared a video which we'll show momentarily, which is much better suited than me to actually tell you about Mano a little bit, introduce him and his achievements in the field. Now, I joined Mano's group about more than 20 years ago, back at ISIS, or IONIS now in California. And, I learned a lot, not only about the science of nucleic acids, but also to be passionate about what we do, our work, to cherish and celebrate the successes, but also the failures, and most importantly, to have fun at what we do. And Mano, I want to thank you for providing this environment. It was awesome, and I'm so proud of you. And, you always reminded us of the giants in the field of nucleic acid chemistry and biology on whose shoulders we stand today, who paved the way. And, like few others, Mano has shaped the field of therapeutic oligonucleotides with his scientific vision, his passion, and his perseverance, even in times of great doubt. So today, I think we stand on Mano's shoulders looking into a world of therapeutic oligonucleotides. So thank you, Mano. And with this, I would like to start the video.
I've known Mano for 20 years. And he is a gentleman scholar. He is a phenomenal scientist, but he's much bigger than the science. He's a colleague, he's a mentor, he is a scientist.
Besides being a phenomenal scientist, he's just an incredibly friendly, nice person. And so, great scientist, but a great friend to me.
Working with Mano has taught me a lot. More than anything, it's his dedication to his science. It's his ability to persist and try and unravel difficult problems. And it's the optimism he has.
He was a brilliant student. Meeting undergraduate BSc special student M. Manoharan was a revelation. And what was more, he was endowed with an insatiable thirst for new knowledge. I knew right away that he can and will go places. I'm happy to be alive today to learn that Muthiah Manoharan has fulfilled all expectations.
Mano's a world-class scientist. He's, in my opinion, the best oligonucleotide chemist in the world, but he's more than that. It's really Mano that's been the intellectual and spiritual drive that helped us solve the delivery challenge. That was our #1 challenge in developing RNAi therapeutics. And due to Mano's efforts, working with scientists and clinicians at Alnylam, there's just people alive that would not be alive if not for Mano's efforts.
What I've learned from Mano is many things, but I think better life through chemistry. He always has looked at chemistry as a solution for therapeutic applications, and being able to speak the language of chemists is so important.
He's always thinking about how to make everybody else's science better. So it's not about himself, it's not about Alnylam, it's about floating all the boats in the RNAi community.
When I think of Mano's contributions to science, there are of course many contributions. If I had to pick one, I particularly think about Mano's pursuit of conjugates as delivery systems for oligonucleotide therapeutics. That led, of course, to the GalNAc conjugate system that he and his team have pioneered.
It was one of the most innovative things that I think has been done in our industry. And Mano was a significant participant in that.
Mano and the team created a really exciting and actually breakthrough delivery system that is going to benefit patients for decades, if not centuries, into the future. It's just a stunning, creative solution to a very significant problem that changed how pharmaceutical chemistry is going to be practiced in the future.
What Mano has taught me has been how to address the tough questions on drug delivery. And I've learned a lot from him, from his tremendous expertise in the medicinal chemistry of oligonucleotides over the years. And he has made me a better scientist as a result of that.
You can imagine the impact that Mano has had in the entire industry, and then most importantly for the patients who benefit from the advancement of this important therapeutic modality. And it would not have happened without Mano. My favorite attribute of Mano is his smile, which is just infectious.
Mano's smile and the laugh is contagious. When he's energized and engaged and bringing that energy to bear and smiles, he transforms rooms, he transforms people, he transforms teams.
Even in our most challenging days, you always had a smile and were positive.
Mano is the most enthusiastic dancer on the floor. I was really impressed, and I feel, wow, not only do I have to step up my science game, but I have to step up my dance game. If there's an award for the most enthusiastic dancer, Mano should get it.
Mano, your work has inspired so many scientists across the world, including myself. You've been a beacon of light to many of us. You've taught so many that science comes first, that every atom matters.
So Mano, I'd like to congratulate you. It's a lifetime of science, it's a lifetime of dedication to chemistry, and it's a lifetime of innovation. Please don't ever stop. Please keep pushing the boundaries.
Mano, I am so proud of your accomplishments, and I feel honored to having seen you think through problem solving and seeing how you got, the field to where it is today. So congratulations, and it's time for celebration.
My congratulations to you, who has helped to shape the oligonucleotide therapeutics field in a superb manner over so many years, not only as a chemist, but also as an integrating person.
Congratulations, Mano. I couldn't be more pleased by this recognition.
You are, without a doubt, a leader in oligonucleotide therapeutic. You are a star in the eyes of all of us that are committed to advancing RNA therapies for patients.
I respect you as a human being, and I'm honored. I'm under my
And then most importantly for the patients who benefit
you. It's a lifetime of science, it's a lifetime of dedication to chemistry, and it's a lifetime of innovation. Please don't ever stop. Please keep pushing the boundaries.
Mano, I am so proud of your accomplishments, and I feel honored to having seen you think through problem solving and seeing how you got, the field to where it is today. So congratulations, and it's time for celebration.
My congratulations to you, who has helped to shape the oligonucleotide therapeutics field in a superb manner over so many years, not only as a chemist, but also as an integrating person.
Congratulations, Mano. I couldn't be more pleased by this recognition.
You are, without a doubt, a leader in oligonucleotide therapeutic. You are a star in the eyes of all of us that are committed to advancing RNA therapies for patients.
I respect you as a human being, and I'm honored. I'm under
It's a bit hard for me to collect myself after Martin's comments and video, but I will try my best. I chose this topic title as the Living in the World of Oligonucleotide Therapeutics because I've seen this field evolving in the past 40 years or so. And when I heard this news from Craig about this award, the thought which came to my mind was, miracle happens every day. Some people think they don't, but they do. And I was just reminded of the Forrest Gump. And I myself think that I'm not a smart man, but I know what passion is. And that the passion is the one which probably places me here. And Martin also referred to this. So compared to the previous three speakers who talked a lot of science and where the direction of the field is going, I take this opportunity to basically make this talk as a Thanksgiving talk. And this is going to be a combination of Thanksgiving and the history of the field and where we should be going and some messages for the youngsters. And I particularly chose the history because some of the youngsters who are fascinated by the field today, they may not know where we came from and what are the dots we had to connect. So with that, I want to thank all of you, and thank you very much. And it is mentioned in various languages from the different parts of the world. And for Rachel, Nandri, Vanakkam. And I want to thank by just reading this because this is the most important slide. I want to thank the Oligonucleotide Therapeutics Society, my mentors, guides, and teachers, colleagues and collaborators, the past and present in all the institutions, and my past students and postdocs and present students and postdocs, not only at ISIS or Al-Nilam, but also back in American College, and also all the students community, whomever I meet outside, when I go and talk to them, I get really an excitement. And obviously the leadership, management, and advisors, where I belong, and as Holly pointed out, more importantly, patients, volunteers, and their families who participated in the clinical programs so that we can celebrate the oligonucleotide success today. Investors who believed in the technology who make this going, and also the industry partners, sometimes who believed in the technology and sometimes who did not believe the technology. And that also, they deserve this thank you. And CROs, CMOs, and oligo reagent providers. And as you know, I'm a chemist, so I know how much pain not only the evaluation community suffers, but also the material providers in terms of the contract research organizations, manufacturing people, GMP facilities, and reagents. And I want to thank them. And my family and friends and who are here. And if I have forgotten anybody, all of you. Thank you very much. And in the Oligonucleotide Therapeutics Society, I've been associated since 2004, 2005 till now. And all these people are being the administrators, the board of directors, and the people who make things happen on a daily basis. And all the details are covered, and those are all shown here, and I want to thank them. And in this picture, you can also see the previous winners of this award. Mike Gate and Fritz Eckstein are also there as part of them. And I'm so delighted that they are here in person. And I know I have got the blessing from Mark Carruthers as well as Stan Krug, one of my mentors. And as I come from Tamil Nadu, I remember always this, having shown that picture of the board of directors who represent the entire world and various parts of the world. I want to remind this phrase, which is 2,500 years old. Yadum Ure Yavarum Kelir. This is written in Tamil, and this means I am a citizen of the world. Everybody on earth is my kith and kin. So we are all related, and the science is developed in Cambridge, Massachusetts, can go and cure people in Bulgaria. It can go into cure people in Japan. So that is the kind of science which is implied in these phrases, which is written 2,500 years ago. And I was connected with this OTS, and I attended the very first meeting which happened in Rockefeller, and we organized the 2012 OTS meeting in Boston. We had a wonderful experience there. It was a great program. Hurricane Sandy thought about it in a different way. But in spite of that, with the help of events people, we managed to run the program and managed to disperse all of us very happy and also in a safe manner. So I want to recollect that, which was a great experience. And as Martin pointed out, we are standing on the shoulders of giants. And these are the people who contributed to the nucleic acid chemistry and nucleic acid structure in various ways. And in this picture, I am thinking this today, how fortunate I am. Except Sir Alexander Todd, I was able to meet and interact with every other person shown in this picture. And I particularly recollect the affection, love, shown by Bob Letzinger, Jack Van Boom, and Nelson Leonard. And I want to thank the organizers from Cambridge, Al-Nilam, who have shown here. And you can see we do celebrate Oktoberfest in Cambridge. And these are our Oktoberfest pictures. And I want to thank my colleagues from Cambridge who have come all the way. I want to thank also particularly Nikki, who did a lot of work in organizing this program. And as we know, I don't need to explain this. This is a very old picture made by Radhika and Mohan for me. We know making oligos is not easy. It's because of the chemistry. It's not drug-like properties. We talked about this all week. But we know now that it's not only the biology problems or chemistry problems, also the making the material. Because I remember early days, people used to ask, how about the scalability? What is the cost of that material? Is that 1 gram is $10,000? How we are going to provide the material and all that? But now we know that we can make, in a single run, 10,000 grams of compounds for just a sense strand or antisense strand. So we are going up to 1 mole scale with all the CMC conditions, expected conditions are met, and we are able to deliver the material to the agencies. So that is not only overcoming the biology challenges, making these drugs as drugs, but on also addressing all the CMC issues. So that is possible. And so in spite of these problems which we saw in 30 years ago, Frank Westheimer was very optimistic. When he wrote this review, he thought phosphates are the heroes. The nature chose phosphates. Phosphates could be the leaving group, could be the nucleophile. So nature plays everything with the phosphates. So nucleic acids are the winners. So he placed phosphorus in the periodic table in a very predominant position. I heard a rumor. The singer, Beyonce, she's writing a song now. Phosphates rule the world. So So with that optimism, there are 8 drugs are approved now. And in these 8 drugs, there are 5 antisense compounds and 2 splice modulation compounds, 1 aptamer compound, 1 siRNA compounds. And thanks to Fritz, these compounds, there are 5 of them are phosphorothioate-containing compounds in this. And we were fortunate, I was fortunate to be associated with the very first compound, vitramine, shown here with the phosphorothioate backbone. And this modification, as you know, invented in 1966, and the oligomers were demonstrated by Wojciech Stek and Jerry Zahn at NIH. And this is your moment of delight when vitramine was approved in 1998. And this is the first antisense compound. And now we know the first RNAi therapeutic is approved in US, EU, Canada, and Japan. And when Craig Mello got this information, he couldn't stop. He started singing, "I'm on the top of the world." And this is the picture showing Craig dancing. So all these things are possible, the success possible because of this word, chemistry, 9-letter word. So I'm going to take a step back, and I want to little bit point out about my history, if you bear with me. I come from a town called Madurai. It's a temple city in south of India. And here you can see these 14 beautiful towers of Madurai. And if you get a chance to go to India, please go to South India also and see these beautiful 14 towers. And this is the towers of this goddess Meenakshi. And this is supposed to have about 30,000 statues in these 14 towers. And this picture inserted shows the goddess Meenakshi getting married. And that's the place where I grew up. In this small apartment where I grew up, I could see these towers every morning when I was studying in the morning and so on. And I was born in 1953, and that's the year of the double helix, which we know. And also, that's the year when Everest was reached for the first time. That shows the human endurance. It happened in 1953. And Staudinger in Germany, for the paper he published in 1920 on the first observations of the polymer and the macromolecules, his Nobel Prize was awarded in 1953. For a simple man like that, like me, I look at these, in 1953, who else is born? It comes to me mind, Kim Basinger was born. And Chairman Xi was born. And Tony Blair was born. So these are the people I can think of in 1953 and get happy about. And with my respect, I want to thank my parents, Dhanalakshmi and Muttaya. And in my family, I was the first one to go to college. My father was a middle school graduate, 8th grade. My mother was an elementary school graduate, 5th grade. But my father is an incredible mathematician. And his death of 87 or so, he could do mathematics in his head. Whatever fractions, whatever you ask him, without using a paper, he can do that mathematics and he will give the answer. And he had this one goal, namely that what he cannot reach, attain, his children should go. And that's what he guided me. And my mother and father, we lived in a small apartment. When the children goes to school, they will give whatever food they had to the children, not worrying about whether they had it for them or not. So thank you, my parents. So I went to this college called American College. It was started by American missionaries. That's the reason it has this name. And I was associated for 10 years in this college in 1968 to 78 because I graduated my master's in 74, and then I was a faculty member in this college. And this is the beautiful chapel on the right side. But I had some wonderful teachers who were trained in this country, who wanted to be teachers in the college, who came back, and Professor Venkatraman and Professor Masilamani, they taught me the chemistry. And they were my head of the departments. And although they appreciated my teaching and all those things, they were insisting, there is a place outside American College, Manos, that you should go and study. So they persuaded and kind of kicked me to write the GRE, and I came here. And my Tamil literature knowledge was given by Professor Solomon Papaya, shown here. And in 1978, I come to this United States, and that is the year of the birth of oligonucleotide therapeutics. And you can see Paul Zemenzenik, for the first time, he published the antisense paper in 1978. And that year, I came to North Carolina as a graduate student. If you don't know North Carolina, and that's the place of Tar Heels, Michael Jordan went to that school. And, interestingly, when I was a graduate student, he was an undergraduate student in the same place. And I joined Professor Ernst Eliel's group. And Professor Ernst Eliel is a German. He moved from Cologne to Chapel Hill. And he wrote the book on stereochemistry of carbon compounds. And in fact, he has written his life history on the Cologne to Chapel Hill. He is a person who left Germany, and during his education, he had to go in during the Second World War time in a boat, not knowing where that boat is going, because he had to just escape. For that reason or so, something like that, he had this interest in teaching international groups. So his group is always an international students group and postdocs. And he gave a lot of freedom for me to learn and contribute. And during my graduate days, student days, he also visited my hometown, Madurai, and visited American College to give a lecture. And this is a picture I cherish because he asked his wife to take a picture with my parents and my brother. And this happened when he gave this Raman lectureship at American College. And I worked with him on the conformation analysis of natural products and the model compounds and the drugs. I won't bother you with this too much details, but this has some connection to the carbohydrates, what I studied later. Namely, in the methyl cyclohexane, the less stable conformer is at the ratio of 1 to 20. But if you change that atom from methylene to oxygen, like in this heteroatom, in this oxane, when you bring this into the carbohydrate type of structures, that immediately changes from 1 to 20 to 1 in 100. So that was a very difficult problem to see how do we determine this conformational free energy. So I had to make a lot of molecules with this carbon-13 by doing the NMR and so on. And this was the reason why I was kind of interested in the kind of structural properties of these molecules. Similarly, when you bring a phenyl group into the cyclohexane, that is 1 in 100. The equatorial phenyl is going on the other side. But if you put the phenyl and methyl together, always phenyl group wants to be axial. It doesn't want to go into the equatorial. So these are the fascinating problems Professor Eliel taught me. And he also kicked me out of the graduate group, saying that you had enough time and go and initiate the next career. And in 1983, two significant events of life happened. I found Selvi, and I started my postdoc career with Professor John Galt, student of Frank Westheimer. And Galt's research group is called Gene Busters. And this is before the time of gene editing, and his group was called Gene Busters because they were working on the nucleases, like staph nuclease and so on and so forth. David Corey knows this very well because we worked with him at that time itself. And so I came to Yale Sterling Labs and then moved on to Maryland. And in 1983, when I started with John, and as Claude Helene has quoted somewhere else, I fell into the nucleic acids chemistry and it remained there ever since. And with John, I studied the DNA repair mechanisms in the DNA. The cytidine deaminase can form the cytidine to uracil, and it has to be replaced and studied. So John wanted to know the mechanism of uracil DNA glycosylase and the further repair of this UV endonuclease 5. This cytidine deaminase, after that, the uracil DNA glycosylate can act on this residue, giving the A-basic site, and this A-basic site can exist in the beta form or the alpha form, and this stars means the carbon-13 containing sugar residues. And these are the days when I was learning oligonucleotide chemistry from John himself. He was an assistant professor. He would stand next to me in the hood, and we will be doing chemistry until 2 a.m. And then he will come back at 8 a.m. in the morning, and he will pour his coffee and start that again. And every day he will be asking in the morning and the evening, what's happening, Mano? So anyway, we solved this problem. Very interestingly, I learned this phosphotriester chemistry, went through this, it's not like making through the machines in those days, and showed the structure of the A-basic sites and how the A-basic structure is repaired by endonuclease 5. And that was the one which led me into my job opportunities. And I joined at Life Coach with Alan Cook, who came from Roche. And Alan had this one interesting property, character, that he will bring the leaders of the field. And I was introduced to Bob Letzinger, Kelvin Ogilvie, Mark Carruthers in a very short period of time. And that's the time when Bob Letzinger has published 2 interesting papers. By showing the cholesterol conjugate, he showed the affecting the HIV virus in the cell culture. And he also published a cationic oligonucleotides. And this taught me a very important lessons for making oligonucleotides as drugs. You need either the grease or the positive charge, or you need both of them. And this got stuck even now, and that is one of the lessons I want to point out. I'm sure the youngsters in the audience, they might have realized this by listening to the various talks in this week, that how many times this works again and again and again. And Bob published this in this kind of earlier on papers. And more or less at the same time, I was exposed also to the drug delivery community, like John Paul Baer and Frank Zoka and that group. And there was also a wonderful paper from Bernard Leblou and showing this polylysine conjugates, how that affects the uptake of oligonucleotides. And in 1986, John Paul Baer pointed out how the synthetic vectors for DNA delivery are important. And he showed the combination of lipids with the positive charges and these aryl groups. And later on, when I met John Paul Baer, he also taught me this concept of proton sponge. Also, that is a very important concept related to what Steve Dowdy is doing today, namely endosomolytic release. And this is some of the things what John Paul Baer discussed with me for over a period of long time. And in 1990, I joined Dan Cook's group at ISIS. And I was interviewed in a room with 5 great people who are the leaders of ISIS, and 2 other great scientists whom I saw there were Stan Crook and Frank Bennett. And over the next 13 years, I learned a lot. And this slide is according to Dan Cook, and he shows the various modifications. And this also shows how he organized the group. He had a group of backbone modifications group, conjugates group, heterocyclic modifications, and so on. It is very interesting when I went there, when he asked me what I want to do, when I mentioned conjugates, he set a group for me. And these are the 3 things which I learned from him over and over again, and for which he is an example himself. There is no substitute for hard work. He will come 4:50 in the morning every day. And the best time to discuss chemistry with him is at 5:30 in the morning. And that that is one thing. And the second thing, he will say, be all you can be. You can be a scientist today, you can be a CSO, you can be a CEO, anything you want. That's something, for some reason, he will tell. And when there is something is down, either in your personal life or in the chemistry, he will say, keep your head up, Mano. So these are the kind of messages he taught me. And he's a great mentor, and all his modifications are shown here. And I learned a lot about the antisense mechanisms from the group at ISIS. And also, as an organic chemist, I was beginning to learn about becoming a medicinal chemistry by learning about this pharmacokinetics. What is this pharmacokinetics and biodistribution? And this is a cartoon which I saw in Richard Geary's office in his book. And this shot is given to this kid who has a sore throat, and he's wondering how this drug is going to get from his rear end shot to his sore throat place. So this was the theme of biodistribution. And this made me think about the pharmacokinetics. And initially, because Dan was focused on these 2' modifications, I started working on the 2' modifications. Our first paper was on the tetrahedron letters. And Masad helped me to review this paper before submission. And that was a big deal in those days in getting the tetraletters papers. So we worked on the 2', 3' carbohydrate modifications for conjugation chemistry. Some of them are shown here. And one of the modifications at that time was the aminopropyl modification, which showed extremely high nucleus resistance from Dan Cook's study. And I started working with Martin Yegley, whom I met in 1996. And Martin helped me to solve the crystal structure of the aminopropyl containing oligonucleotides. And he explained to me how this metal cofactor displacement by the aminopropyl groups can protect this against the nucleases. And that was the time I got connected with this, the structure-based understanding of these chemical modifications. This led into the other 2' modifications, what we studied, including this lipid nucleic acid modifications at the 2' position. And in this paper, interestingly, in 1995, we called this as lipidic nucleic acids. And 1998 was the time LNA came, and LNA was the term which is given for this locked nucleic acids. We didn't think about it during this lipidic nucleic acids time. And when we studied about these lipidic nucleic acids over the period of time, the next 10 years or so, we understood that provide the free uptake of oligos, they alter improved biodistribution of the oligos, and improved liver uptake, and then improved the pharmacology. These were the advantages we learned and reviewed in the previous generation of this nucleic acid therapeutics journal. And there was this celebrated methoxyethyl. And this methoxyethyl group was needed because this first generation phosphorothioate oligos for the CRAF, PKC alpha, and various other compounds failed. And this methoxyethyl was a savior. And this was invented with the thinking that maybe we can make them with the nucleus resistance with the high receptor affinity, and so that we can make the RNA mimetics. And again, with discussing with Martin Yegley, we explained the rationale why these molecules have this high binding affinity and why they have this very high nucleus resistance. This is because of the gauche effect and water of hydration. This protects that phosphate and increases the RNA binding. And this is a very important contribution from Yegley's lab based on the structure work we did together. But just like the talk we heard from Leong earlier on, even at that time, at the thinking at ISIS in 1998 was the reduction of the PS to PO substitution would improve the safety profile. So reduce the immune stimulation, reduce the anticoagulant effect on complement activation. But how do we have, when we have the diester, how do we avoid this renal fast clearance? So this was the thinking there was, and for that one, with Richard Geary and Art Levin, we made this comparison of the full Mo phosphodiester with the full Mo phosphorothioate. And we made this alternating POPS where we can do this modulation of extreme clearance for the diester and the improved liver to kidney ratio in the phosphorothioates that we can modulate the pharmacokinetics. So this was something which got stuck in my mind at that time, namely one can play around with the backbone in terms of altering the PK properties. And we invested in the lot of 2' modifications at that following years, and we called them as the new kids on the block. And to keep them the Mo as a diester, we wanted to introduce the corresponding sulfur analog shown here. We called this as the MTE, and there are numerous modifications which the structural work again done with Egley's group, and we published. Some of the interesting modifications in this were done based on the discussions what I had with Bruce Ross. When I was keep on making the 2' modifications, he would point out, if you build it, they will come. So you don't need to wait for the evaluation. Just to make it, we will get them tested. So with that, we made a lot of modifications. And this is one of the interesting modifications, combining the nuclease resistance properties of the aminopropo with the gauche effect of the Mo, and which showed the combination of properties in this DMA-EOE, which was done by Maria and Prakash. And another one, which is another exciting modification like the Mo, is this NMA modification. And this was done by Andy and Prakash. And this shown that they are having the equivalent effect like this Mo, and published subsequently. How about the G-clamp? G-clamp was the inspiration from Mark Matucci for me at that time. And in Mark, what he showed was there could be, instead of when you bring a G-clamp, which is a C-mimic, one can have 4 hydrogen bonds, just like the lysine would react in the backbone of the phosphates using the 2 nitrogen groups. So he showed that 4 hydrogen bonds. So we asked ourselves, Martin was in the lab at the time, we were asking our Martin Meyer, we asked the question, can we make 5 hydrogen bonds? If Matucci can make the 4 hydrogen bonds, namely, instead of making it like a lysine, can we make it like an arginine, so we would reach the O6 as well as the N7 positions? And with that, we did make the guanidinium compound of the G-clamp. And interestingly, we were able to make the crystal structure with that modification. And I think, and I want this to be corrected, this is the only structure known where the 5 hydrogen bonded system has been shown in the literature. You can see here there are 3 hydrogen bonds between the G and C, one from the O6 and one from the N7. So these 5 hydrogen bonds shown at the 1 angstrom resolution by Martin Egley. And in the PNA area, we were asking the G-clamp, Matucci showed 18 degrees increase. We wanted to ask the question, how high is really high? So Rajiv, at that time, Rajiv and Martin, we made this very synthetic, challenging molecule with the G-clamp attached to the PNA backbone, and we showed we can go up to 24 degrees per modification. Single modification change the delta Tm 24 degrees. And this is another very exciting stage in our career for Rajiv and me. And this is because I worry also about the synthesis of oligonucleotides. I want to point out the birth of the unilinker. Unilinker is used universally now in various laboratories, whether it is a small scale or in the manufacturing scale. This is the birth of the unilinker. One day, Andrei Gusayev, who was working with me, he came to my office and said, Mano, we should do something about making this phosphoramidite-free 3' end. And he described and he explained what his thoughts are. And that was the origin of this unilinker. Until now, I'm thinking about it. This is a great chemistry came from Andre. And this is, I'm pointing out for the pride associated with making it, and also for encouraging my younger colleague who had a great idea. And I told Andre, let's do it. So that's what we did, and we evaluated the kinetics, and we showed that it shows the facile cleavage at the 3' end, so that we could form this unilinker. And this is a great synthetic help for the oligonucleotide chemists now. And how about the conjugates? We were always interested in this, and we were doing this conjugation at the cholesterol, ibuprofen, folic acid, and galnac, even at alnylam, even at ISIS. And the carbohydrate clusters for hepatocyte targeting was influenced because Y.C. Lee at Johns Hopkins, he showed this. This could be targeting for the ASGPR receptor. And I wanted to make that effort, but we didn't have enough synthesis help. So we approached George Just, and George Just at McGill helped me make this compound. And Martin in our group, he oligomerized it, and he had to identify the right kind of solid support, and he suffered through this. And he made this, and here is the model of this Martin Mohan showing the tripod nature of this trivalent galnac. So at that time, we were able to go only to the synthesis aspect of this. And another component, apart from Y.C. Lee's work and the ASCLO glycoprotein receptor, was the inspiring work by Jack Van Boom. I mentioned to you, whenever I had a chance to talk to Jack, he will always, for some reason, he enjoyed talking chemistry. So just sitting and listening to him made me think about all the ways he did his molecules. So that was an inspiration in building this choline-based galnac cluster, but unfortunately we couldn't test it in vivo at that time because we couldn't make it enough, and there was no reason beyond these phosphorothioates at that time. And similarly, we made the folate conjugates, and folate conjugates is another synthesis problem because we had a different carboxylates, and we had to go through this folate receptor and to target the cancer cells. Fortunately, Balbat and Andre and Geeti Balo solved this problem, and we came up with how do we come up with this folate deprotection conditions using 1 molar aqueous piperidine. And this was another turning point in terms of this folate conjugates field. And coming back to this cholesterol conjugate, we took the phosphodiester containing compound, totally phosphodiester, attached to cholesterol, and we saw that increased plasma concentration, and compared to the phosphodiester molecule, which goes totally into the kidney, not much into the other tissues. And you can see this is not in the scale, it's going out of the scale. When we make this phosphodiester with the cholesterol, we were able to distribute in a kind of a broad manner. So this was the kind of a hidden in my head that when there is a diester molecule, by bringing a lipophilic molecule, you will be able to deliver to liver and other tissues. So that's what the conjugations area, what we did. And in 2003, we had to say goodbye to Carlsbad, and with this fade pictures, with the but bright memories, and with these two superstars with whom I worked, and I left, and I moved on to Cambridge, Massachusetts. And in this meantime, we also organized Pacific Chem meeting because we were also interested in organizing oligonucleotide chemistry meetings outside. And here you can see the celebration we had for the 80th birthday for Bob Letzinger in Honolulu, organized by Masadama. And you can see also Paul Miller here, and and Chris Wiles. So on February 2003, from Carlsbad, California to Cambridge, Massachusetts. And this was literally the case when I landed out of the flight. And I was not sure whether I wanted to go to my room or go back to Carlsbad. And we were in the 790 Memorial Drive, and fortunately we had a great group with Rajiv and Klaus, Akin, Kesavan, Sumi, and Gary. So we started our journey. And we were able to, along working with the Alnylam AG, we were able to show the first therapeutic silencing with systemic RNAi with the lipid nucleic acids, namely the cholesterol conjugates, in silencing ApoB. And we were able to show the RNAi effect by the 5' race. And we also, working with Marcus Teufel, we were able to demonstrate this works by LDL, HDL, and albumin binding of the conjugates. And at that time, this was considered as the breakthrough. So CNE News wrote a write-up about this gene silencer special delivery. And we evaluated a series of lipid molecules, and along with the Alnylam AG group and with the Stoffel group. Another thing which I want to point out, both from the management side and also for the youngster side, is this concept called kinetomia. Kinetomia is a Greek word. Our CEO, John Maraganore, is a Greek. He loves this word. And this means innovation. Because we discussed this concept of microRNAs and microRNA silencing during a lunch in a SAB meeting. And Marcus was wondering, how do we silence the microRNA? And he mentioned about microRNA 122. And he also mentioned that it is in liver. The answer was very obvious to me. Just put the cholesterol. So we wrote it in a napkin. And we didn't discuss this with our management. But the concept of kinetomia comes because this Greek man, he gives the time to do anything you want outside the time. You can do in the weekend, evenings, and so on. So with Ravi and Rajiv, we were able to make the conjugate, and we were able to show the silencing of microRNAs. And we called this as the antagomers. So the why I wanted to point out is, if there is some resistance from others, just to do it on your time. Weekends are there, evenings are there, anytime you want. You just can go. And when the result comes, when you take it to the result to the PI, they're going to say, oh, I thought about that. So you do it. And we took this lipophilic molecules for mutant Huntington with Neil Aronin's group and Phil Zamore, and also we wanted, with the Dinah Shah's group, we wanted to explore the CNS delivery and Medtronic's collaboration, and also with Judy Lieberman and Deborah Palliser, we were exploring for the local applications of the cholesterol conjugates. But as a company, we had to focus on something. So John Maraganore pointed out, let's think about the strategy for delivery. And that strategy was delivery to liver, John Maraganore's strategy. So now we know that we have 3 pillars for this strategy, namely chemically modified siRNAs and lipid nanoparticles by IV administration, and the GalNAc conjugates for subcutaneous administration. And we know that lipid nanoparticles work beautifully, and we have seen this mechanism several times during the week, so I won't want to take your time. But these lipid nanoparticles led us into the approval of the Onpattro. And lipid nanoparticles consist of 2 new entities, namely MC3 and the PEG-DMG. This PEG-DMG, I will quickly point out, we made this compound after analyzing about 15 different constructs containing esters, carbamates, ethers, and so on and so forth. And this construct, we made them also chirally pure in the R form. And we also, working with the Alcana and Peter Cullis groups, and also with Bob Langer's groups, we decided to choose this MC3 from a SAR study of about 350 lipids. And you can, now coming back to the siRNA itself, you can see this is not fully modified. This is still an RNA. What this Hans Peters group used to call this as the endo-light variation. It's the 2'-O-methyl reduces the immune stimulations, no phosphorothioates. And these are packed into this Trojan horse like this lipid nanoparticles, and that effectively delivers Onpattro. And we heard so much about the TTR amyloidosis, so I don't need to go into the details, and also in the interest of time. So what I will point out is this came from a gene walk. It's a small gene, started with the analysis of 669 molecules, and which were reduced to synthesizing 137 molecules, and finally coming up with the siRNAs with the picomolar inhibitor quality. And that one was, this shows the gene walk profile of this compounds done at that time in Rachel's group. And I mentioned about 350 lipids SAR. We started in this program with this Delin DMA modification, and when we came out of this study, we chose this MC3 modifications. And in these cases, we used consistently this factor 7 assay. The factor 7 assay is a gift of Akin Akinch to the lab, and this was used by the entire people in the field for evaluating lipid nanoparticles delivery. And this is, you can see this shift towards the left side, and it becomes like this micrograms per kilogram dose. And we chose this molecule, Delin DMA, which is, I'm just pointing out one other significant historical point. When we chose the unoptimized, the first generation lipid, Delin DMA, we chose this for the phase 1 study. We saw only 40% gene silencing. But when we look into the individual patient's case, there was one patient who showed the 80% knockdown. And that was our foothold. At that time, there was, this molecule can do miracles. This was the hope. And we chose that hope. We kept the siRNA, decided to work on the SAR of these lipids. And that was the way this lipid SAR continued, and various lipids were evaluated. And this is another important paper published by MJ in the Anguande Chemie. This is shows the pKa studies of about 57 lipids and their efficacy in knocking down these factor 7 levels. And here is the MC3, and that is the one which is most effective. And once this MC3 was decided, within 2 weeks, MJ was able to make it and scale it up, and he kept it ready for doing the other studies. So that was a turning point. And I have a quiz for the youngsters in the audience. Lipids, when we have a tertiary nitrogen like this, they have this pKa of 10.2. But in the lipid nanoparticles, their head group has a pKa of 6.4. Why is that? And the origin of the answers lies in the understanding of proteins containing lysine groups, and answered by Frank Westheimer and John Galt over the period of 1971, 95, and 96. Please understand this field effect. So this one was taken, the MC3 was taken, and we made the PEG DMG, and as they say, the rest is history. And this is the mechanism, namely when lipid nanoparticles is entered, it picks up the ApoE, and the ApoE targets the lipid, LDL receptors that internalizes the head group pKa of 6.4, brings the proton sponge, what John Paul Baer talked about, in the endosomes, and that leads into this endosomalytic release and successful release of these lipid nanoparticles. And this is the freedom realized. So that was the success of the lipid nanoparticles, and this was proven by the corresponding clinical studies. You can see this when we changed this into the MC3, we were able to see 90% knockdown, and this was translated into the phase 3 studies over a period of 18 months in a 250 patients study. Very nicely TTR knockdown that resulted nicely in the clinical advantage by measuring this MNIS+7 score or the Norfolk quality of life. So people who are getting the placebo, they don't respond. This keeps on increasing. People getting the drug, they are getting cured. And there are a lot of videos available for the people who are really getting the drug on Patro. And it is really emotional to go there, seeing there what this nucleic acid-based therapy means. And that is really wonderful. Now, where we are in the lipid nanoparticles, we moved from the MC3 into rapidly eliminating lipid nanoparticles having the ester ends, and that's where we are moving forward with. I know I'm past my time, but I have to talk about GalNAc chemistry. So from the lipid nanoparticles, we finished this work with this great team, with the great work and great outcome. And you can see this is the 3 teams, the UBC and Alcana teams, MIT team, UCLA Mike Jung, advisor, and the Alnylam team. So at that time, there was one person assisted by 2 other individuals in the 3rd floor corner. They were saying, where are those conjugates? Conjugates. So we brought back the conjugates, and after long ups and downs, a lot of synthetic challenges, we were able to show that it works, and it also works by subcutaneous administration. And this is the mechanism. You have seen it in various places here in this meeting, and that's our summary of our publications. And this is a beautiful natural mechanism, and I always wonder how clever this nature is. And I also sometimes admire, this is the best God's gift for this acylglycoprotein receptor GalNAc system, because so effectively takes into the liver hepatocytes in a very fast mode. But when we make a naked molecule, siRNAs, even with the chemical modifications and attach GalNAc, there are 2 problems. One is the metabolic stability. The second one is, by looking at this trivalent GalNAc, people have asked, are you going to make this molecule in a reasonable amount of material? So we had to address that problem, and we had to address both these problems, namely, how do we make them metabolically more stable? And Anastasia mentioned on the other day, this is the time when we say, okay, keep calm and do chemistry. And that's what we did to address the problems of metabolic stability, maintaining the potency, maintaining the specificity, maintaining the safety. And that led into a lot of chemical modifications. And this is the crew which made this first 1 kilo of GalNAc support in our lab. And that solved the problem of the scalability issues, because this requires 25-step synthesis. And it was a kind of a very consistent effort by this tireless team. I didn't do anything. And this team demonstrated that it is possible. And then we also made a lot of chemical modifications, which are shown here in these various publications. And you heard also about these various modifications needed for the function of these siRNAs in this meeting. So in the interest of time, I don't want to go into those details. But these chemistries keep coming. So with that one, we were able to address the metabolic stability issues and scalabilities. And in this one also, we have various generation of the GalNAc conjugates. We have the revusiran type conjugate, namely the standard template chemistry conjugate, and then we have the ESC chemistry, enhanced stabilization chemistry conjugate. And we also now have this enhanced stabilization chemistry plus conjugate, where we are very carefully monitoring the increased specificity. So these are the various steps involved with the subcutaneous administration of this GalNAc conjugate. We were able to build from our portfolio of chemical modifications. And this GNA chemistry, whom you heard this yesterday from Martin Yegley. You might have seen Mark Slagle's poster. And this is a great thermodynamic modulator of off-target mitigation when placed into the seed region. And there were some nice papers from Alnylam on this. And I will point out two quick examples. By taking the TTR subcutaneous compound, this is a 25 milligram single dose, which extends the silencing of TTR over a period of 320 days. So this is a single dose with great safety parameters, no SAEs, no discontinuations, and so on. This shows, again, the power of chemistry with this GalNAc delivery system. This is the vutrisiran opportunity. And you heard this from the PCSK9 example in this meeting already. And PCSK9 is a problem in the hypercholesterolemia phase because PCSK9 eats LDL receptor, and LDL receptor on disappearance cannot deal with the LDL cholesterol, and so we have to stop synthesis of PCSK9. And this works so nicely, and you will hear about this more again tomorrow, so I will give you just one slide showing the Orion 11 results. And this shows the effective after 300 milligram total dose. The first dose after 3 months, second dose, once every 6 months dose, PCSK9, 300 milligram total dose, you see the reduction of 54% LDL cholesterol. And I'm a person who takes statin, and I'm waiting for this approval of this drug because I can take once every 6 months injection. And I don't need to take 80 milligrams of Lipitor every day. And I call this as this gene editing with RNAi, because you just need the treatment once every 6 months. We have an extensive pipeline at Alnylam based on the GalNAc chemical modifications, and there are about 10 compounds. This is in our website, and most of you know about this already. There is one other compound which you will hear the details again tomorrow, is this how this givosiran controls the porphyria. And this porphyria is the sadness, the drug, the problem associated with the King George III. And also there was a recent review by the patient who was getting this treatment and pointing out is how givosiran is life-changing. And unfortunately, in the interest of time, and also because you heard so much about the CNS and other applications, I won't be talking about it, but we will be disclosing and describing a lot about the CNS applications of conjugation chemistry and applications in the ocular field in the coming meetings. So Alnylam has expanded going beyond liver. And these are, please bear with me for the next 5 minutes or so, because I want to conclude this in some way, what are my thoughts are. In 2003, in an interview, RNAi was described as, this is a gift from heaven by Phil Sharp. And now, I think we can confidently say that we have addressed the liver problem. Now we are moving into the eye and brain and other tissues. And I like this statement by Churchill. This is not the end. This is not even the beginning of the end. This is just perhaps the end of the beginning for the nucleic acid therapeutics. And these are some personal things which I wrote. This is one of the things which asked to any chemist, and this is again a quote. in general, the question asked of any chemist is, what have you done for us today or lately? That's okay, man. And the answer is, this is a quote from Craig Mello from in one of his articles. I'm still turning over stones, hoping to find something new. And what are those something new could be? What are the undruggable diseases where we can go with this nucleic acids platform? And where we can apply the GalNAc conjugates in different applications. We have shown beautifully how we can control the silencing with the reversiers. Are there applications like reversiers where we can apply? And what novel chemical modification will next revolutionize the field? I consider phosphorothioate, 2'-fluoro, MO, LNA. These are really revolutionizing modifications. Where is the next one? Who is bringing that modification? And are there other alternatives than doing the solid phase phosphoramidite chemistries? Can you make this in really ton scale? When the PCSK9 is needed in ton scale, can you make it? Is a solution phase available? Is a peptide-based synthesis, is that available? And as I mentioned, we are just in the end of the beginning. How do we achieve efficient delivery to the other tissues? Are there other ligand receptor pairs applicable? And with Steve, we talk about how do we achieve endosomalytic release of the oligonucleotides. In spite of these LNPs and everything is working, there are only 1 or 2% we are getting out. So again, John Paul Baer, in his 1993 review, he asked this question. Yet rough calculation shows there are still three orders of magnitude to go into delivery. So this is John Paul's quote, not mine. Chemists, back to the bench. Do more work, man. So this is another important point in this 40-year journey of the nucleic acids field, because I reminded of we had this wonderful tree, now it's giving this fruition, going into the rare diseases, genetic diseases, metabolic diseases, and all these things. But like Herb Brown pointed out in his Nobel lecture, tall oaks all start from little acorns, like this nucleic acid therapeutics field. And he says the acorn was a mere grain of pollen. The grain of pollen developed first into an acorn, and then acorn became an oak. The oak tree became a forest. Now we are beginning to see the outlines of a continent by this oligonucleotide therapeutics. But still, it's evident that we have only searched the surface. It will take another generation of scientists, like the youngsters here, to settle that continent to utilize for the good of mankind. So let us go and use this technology. I want to thank all my collaborators and colleagues who worked with me at Alnylam over the past 16 years. Same thing with my colleagues and mentors and collaborators from ISIS days. And these are some of the pictures from Alnylam. Here you can see these various time points, 2007, 2012, and when Fritz and Marv visited during the Alnylam 10-year anniversary, this picture was taken. And Mike Jung is here, and this is a recent picture from the postdocs and students, and you can see this evolution of these various generations of colleagues. And I want to thank also our Alnylam AG, the Hans Peter, Philip, and Ingo, and the other junior members. We also have an exciting science summer intern program. You can see some of our summer interns also in this picture, and some of the colleagues who left and moved on to the other companies. And finally, I want to thank my family, and they are shown here. And particularly, I want to express my deep gratitude and love to my wife, Selvi, because she had the time and patience to let me go. She never knew when I would leave and when I would come back, but she was there for me for always with a big smile. Thank you, and thank you, Dan, and thank you, Mohan. And as seen here, you know, I have done some dancing with John Marganori. In dancing with John Marganori in 2007, he said, this is the move, but that's the place where we have to go. And that's what he showed. And in 2006, he's doing it still. And here is Akshay trying to do this dancing. And Barry Green tells me you can dance, but also there is life in other than dance. And this is in the gym. He's doing this ninja workout. And these are the OTS meeting dance. And I hope you will enjoy such a dance this evening. And here you can see. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you very much. Thank you.
Okay, well, in view of time, you used up all the question times and more.
Well, we will discuss this during the lunch.
You can discuss during the dancing.
Yes.
I'm going to hand over the...
Thank you very much. Okay, good. Thank you very much. Good.
Okay, before we all leave, there's two more things I want to say. The first thing, which I forgot, is that our junior board member, Erin McConnell, was actually involved and coordinated all of us jury members to make sure we evaluated everything on time. So many thanks to her, much appreciated. You just heard Mano's Lifetime Achievement Award talk. The nominations for next year's Lifetime Achievement Award winner are now open. And Lifetime Achievement Award suggests that maybe you can only nominate people who are advanced in age, to put it like that. We want to stress that anyone who made a good impact to the field, an important impact to the field, and this can be one thing or multiple consecutive things, you can consider them for nomination. So more information will follow. You will get instructions in your inbox, and you can then read all the criteria related to nominations, and also information on how you can nominate people to give the Lifetime Achievement Award lecture next year. So we have a lunch break now. We are slightly late. You have Mano to thank for that. But I think we all agree that it was a great talk, so I don't personally care that much. The award winners can't rush off to dinner yet, or to lunch yet, because we're going to take pictures. Everyone else, please enjoy your lunch. We will start again at 2:30.